Hello, MATSE 112. I hope you're having a good Monday so far. So sorry I can't be with you today, but I'm going to make this little video to give you some hints on how to approach the thermodynamics problems for the upcoming test on Friday. Raymond and Clara are going to give you some practice problems, and then we'll continue our review on Wednesday. So please bring your questions, or please email me with questions. So I'm not at Penn State today. I'm in Monterey, California at a conference talking about how polymer science can contribute to the development of alternative energy sources, including fuel cells and also advanced batteries. Here's a beautiful image of Monterey Bay. So that's Monterey Bay right there and the Pacific Ocean. So when you go and talk science, it's always nice to talk science in pleasant surroundings, and so that's why I'm here today. So what I want to talk about is how to navigate these thermodynamics problems that you're going to be working on for your homework and that are going to be on the exam. So I will post these slides and you can take a look at them. But this sort of gives you a roadmap for what you might look for or how you might approach the various problems in this unit that you're going to take the exam for on Friday. So first of all, you need to figure out whether this is a calorimetry problem or whether it's a systems and surroundings problem and how to draw that diagram. So you'll have problems of both types, and this diagram is really helpful for whether you're having heat and work exchanged between the system and the surroundings, and that should look familiar to you so you can fill in what the system is and what the surroundings is and the resulting variables. Of course, the surroundings temperature never changes, and so we discussed that in the last class, and so that's something to keep in mind. And then we also have calorimetry problems where we're exchanging heat between two objects. So you can have heat flow between two different objects, so something is heating up, something else is cooling down. And so knowing the difference between whether you have a systems and surroundings problem or whether you have a calorimetry problem is really important to start to approach these problems in the right manner. So things you want to think about are, do you know the temperatures or the final and initial temperatures? So what temperatures are available for you in the problem statement? Do you know the heat capacity? So is there data given on the heat capacity of the system or the heat capacity of the various phases in a calorimetry problem? Are there heats of reaction involved, or a chemical reaction that's exo or endothermic, and so it absorbs or evolves heat? Same with the phase change. Is there melting or solidification, and you can track the heat through the heats of fusion or the heats of evaporation. What are the heat and work flows? And that really works for either of these setups, and so how do you calculate Q is a really important concept. And then, is there an expression for what's happening with W? What's going on with the work? And how do Q and W relate to the change in internal energy? Is there information given for delta G or KEQ or other thermodynamic variables that you know allow you to calculate some heat or workflow in either of these problems? Also, it's important to keep in mind in terms of what is the physical process. So this bottom bullet point gives you a reality check as you start to approach these problems. And so what's really physically happening? What's happening when liquid water solidifies to solid water? Or what's happening when this chemical reaction occurs? Is heat being evolved or is heat being absorbed? Does the temperature go up or down? And is that temperature change reasonable? And so you really, before you approach the nitty-gritty of solving the equations and giving me an answer with units, try and think about exactly what's going on in the problem and try and make sense of it in terms of a temperature change or the reasonableness of the physical process. And it's important to make sure you have that grip on reality before you start to get into the details of how to solve these problems. So for a calorimetry problem, you should think about what is heating up and what is cooling down. How do you know which is which? Well, let me get back to the slide here. How do you know what's heating up? How do you know what's cooling down? What direction is the heat moving? How is energy exchanged between the two bodies in a calorimetry problem? Sorry, I'm having issues with my display here. And so keeping an idea of what's the final temperature here, what's the initial temperature, what's heating up, what's cooling down, all of those things give you a basis in reality for how to approach calorimetry problems. And then the math is rather easy. Q equals mCp delta T. Make sure you look at the units carefully. Sometimes mass and Cp are combined. So if we have a calorimeter with a certain heat capacity, sometimes you don't know what the mass of that calorimeter is. You just know how much it'll heat up or cool down as a function of the heat. And so look very carefully at the units. Sometimes we know the calorimeter is made out of iron or the calorimeter is made out of water. And so you can use mCp delta T effectively, but make sure the units work. Q is always in joules. And so as we track these heat and workflows, we want to make sure that the units work out. Do we have a constant volume calorimeter or do we have a constant pressure calorimeter? And you should know the difference between those two different types of calorimeters and what information they give you. And is your answer reasonable? So if there's a heat transfer problem, you should be able to bound the temperature change of the different phases in a reasonable level and make sure that you go back and check. So once you know the temperature changes of each phase, you can say, does my heat flow balance? Is the Q the same in each phase? And can I make sense of what's happening? So make sure you give me reasonable answers and are able to bound your answers with units, of course, in these problems. And now if we have a thermodynamics problem in terms of system and surroundings, or the thermodynamic variables, delta G, delta H, and delta S, it's really important to think about how I get to these different thermodynamic quantities. So I always have an expression for KEQ as it relates to delta G0. I can also write down Q, so the reaction quotient, I can write that at any time if I'm given concentrations, and how Q relates to KEQ. And then I also have a couple of equations that I always know are true. Delta G equals delta H minus T delta S. I know how to get the delta G's of reactions, or the delta H's, or the delta S's. And so writing down equations that I know are true, and also writing down what I'm targeting. So if I'm asking a question about equilibrium, I want to have some way to get to the equilibrium constant, or some way to get to delta G0. If I'm asking a question about forward or reverse direction in a reaction, or is this reaction at equilibrium, I probably want to know what the equilibrium constant is, or at least know what the sign of delta G is. And so make sure you can move around these different variables by writing down what you know, and by writing down equations that seem reasonable to try and approach the thermodynamic variables that will give you the answer you're looking for. Finally, if it's an entropy question, which we've covered in the last couple of classes, but is still probably yet to be revealed fully to you in terms of understanding, is make sure you stick with the entropy equations that we know. So we have one equation for the delta S of reaction, or the delta S0, the sum of the delta S of the products minus the sum of the delta S of the reactants. But we also have ways to calculate the entropy based on the heat flow over the temperature. So we know how to calculate the entropy of the surroundings. In some cases, we know how to calculate the entropy of the system based on this equation. And we know how to bound our answer, or at least estimate our answer, in terms of whether it's a reversible isothermal phase change process, or whether we have some irreversible process where the delta S of the universe has to be greater than 0. So the equations that I've shown you in these PowerPoint slides give you some idea of how to approach these thermodynamic problems using equations that are true, using concepts that you know, and then being able to navigate through these different thermodynamic variables. That might help you, especially if you're stuck, or especially if you don't know how to approach a problem. This will give you some tools or a flow diagram to help you figure out what's going on. Finally, my advice always is to study the homework examples and learn how to navigate through these different thermodynamic variables and equations, generally given the problem statements or given the information that you're given in the problem to help get started. So Clara and Raymond will give you some exercises to do in class. Please do these by yourself. Consider it a short practice test. I will go over all of these answers on Wednesday, so the answers will be posted on Canvas as well to help your studying. But why don't you treat this next on-paper exercise as a practice test to help you get warmed up for thinking about how to solve these problems quickly, for helping you get to finding the answers quickly and writing them down with units and good answers in boxes so it's very clear as to what your process was. So please put your name on these assignments, do them by yourself, and then once you're finished with answers, please hand them in to Clara and Raymond, and good luck studying in the next couple days. I will see you in person on Wednesday, and please email with any questions or problems that you may have. Thank you very much, and I'll see you soon.